Assalamu alaikum. I welcome you all to a new lecture in NS224 numerical analysis. This is Said Ibrahim, your numerical analysis teacher. In today's lecture, we are going to discuss the order of convergency of Newton Raphson method and the order of convergency of secant and Regula Falsi method, method of false position. As we have discussed previously that Newton Raphson method is very fastly converging method, so that's why the because the order of convergency of the Newton Raphson method is 2 and the order of convergency of secant method and Regula Falsi method is 1.62. Yeah, and the scheme of secant and Regula Falsi method is quite similar. So the procedure is different, but the scheme is same. So that's why the order of convergency of both the method is same. Let us start from the order of convergency definition. So as we have defined previously in the previous lecture, that the order of convergency of a method tell us how fastly the method converges toward the root of the function. So generally an iterative method is said to be of order p or has the rate of convergency of the method is p if p is the largest positive real number for which the en plus 1 term absolute is less than or equal to c times c is any constant. C may be 1, 2, 3, 4. C is an arbitrary real number. En absolute whole raised to the power p, where en represent the error in the nth term in the nth iteration, and r is the exact root of the function if we can find the exact root of the function. So the order of convergency of Newton-Raphson method. So as we know that the Newton-Raphson method has second order of convergency. So to prove that the Newton-Raphson method has second order of convergency, taking the scheme of the Newton-Raphson method through which we can find the root of the function by substituting n is equal to 0, 1, 2, 3 for n. For x naught will be our initial guess, and for n is equal to 0 we will get x1, for n is equal to 1 we will get x2, and for n is equal to 3 and so on. In the same way we will get the our iteration terms by terms. So this is the scheme of Newton-Raphson method. Consider that r is a simple root or the root of the function in the interval ab, and en is the error in the nth approximation in the Newton-Raphson method. Since we know that the error is the actual value means that the exact root minus the current value means the approximate root, and the actual value means the exact root of the function. So the current root, the approximate value minus the exact value give us the error. So we will compare the nth iteration value. At the nth iteration, what we have an approximation to the root minus actual value. It will give us the error. So from here we can find the value of xn by shifting this r to the left side. We will get xn is equal to en plus r, and by replacing n by n plus 1, what will we get? Xn plus 1 will be equal to x en plus 1. En plus 1 will be the error in the n plus 1th term, in the n plus 1th iteration, the error in the n plus 1th iteration approximation. So now putting in equation number 1 in this scheme of the Newton-Raphson method, what will we get? We will replace xn plus 1 by en plus 1 plus r, and xn by en plus r, xn by en plus r, and en plus r. Now let us expand it by uh, let us expand these f of en plus r and f prime of en plus r with the help of Taylor series. So after expanding it, we will get these two terms. Now here we will get in the prime, and because we have f prime of en plus r, so with the help of Taylor series we can expand it in that way. Since r is the root of f of x is equal to 0 is the root of the simple root or the exact root of the function, so f of r must be 0, so this term will become 0. After substituting these f of r is equal to 0, we will get this. And after taking f prime of r from these all terms, what will we get? We will get en plus en square divided by 2 factorial into f double prime of r. This term will be the same, and we have take f prime of r common. So if you multiply f prime of r with this term, you will get en into f prime of r, and when you multiply this with this, the f prime of r will be cancelled out with f prime of r, and again we will get this term. And in the same way we will get the same by multiplying this f prime of r, and from here as well we can take f prime of r common. So we will get 1 plus en into f prime of r. After multiplying this f prime of r into these all terms, we will get this again. Let us see. We can take we are going to neglect all the terms having e cube or having more power than 3, because error is a smallest term, and after multiplying a smallest term with some numbers you will get a small number, and a very small number can be neglected. So we have neglected the terms having the error cube and more than this. So after neglecting this term, we can take this denominator to this side by here the power of this whole term is 1. After shifting it to numerator, we will get the power will become negative, and we have a result that if you have 1 plus x whole power minus 1, then you can expand it, and I will show you the result. How can we expand it? We can expand it by the binomial theorem, that 1 plus x power minus 1 will be equal to 1 minus x plus x square minus x cube plus and so on. So after expanding these two by considering these whole term as x and neglecting the terms having en cube and greater than cube, we will get this, and the result is this one result. By with the help of this one result, after expanding 1 plus x whole power minus 1 using binomial expansion, we will get 1 minus x minus plus x square minus x cube. And here remember, we have neglected all those terms having en cube and more power. Now once again multiplying these two terms and neglecting the en cube term and greater, we will get here that en plus 1 is equal to en minus en square. But once again remember that we have neglected all those terms having en cube and greater power. En plus 1, after multiplying this minus sign into this term, we will get minus en, and multiplying minus minus will become positive and plus minus will become. So these two terms can be cancelled out. After cancelling these two terms and taking f double prime of r divided by f prime of r from these two terms common with en square, what will we get? If we take these whole terms common from this term, we will get 1, and by taking f double prime of r divided by f prime of r into 1 over, into en square, we will get 1 over 2. So 1 minus 1 over 2, after taking LCM, we will get 1 divided by 2, and here by after taking the absolute, you will get en square, where the value of p is 2. So after substituting r in f double prime of r and f prime of r, you will get a constant value, and a constant value multiplied by a constant, another constant, you will get a constant, once again a constant value. So if we consider it that this value is some constant c, so we will get en plus 1 absolute is equal to c absolute into en absolute whole power 2. By the definition of the convergency, this represents that the scheme has the second order of convergency. So this was the proof of the order of convergency of Newton Raphson method. As I told you that the bisection method has first order of convergency, which is very slowly converging method. The fixed point iteration method, the order of convergency of the fixed point iteration method is arbitrary. It depends upon the system generating function. So it may be 1, 2, 3, or more. It may be the fastly converging or the very slow converging method, but it depends upon the function, the system generating function. And the Newton-Raphson method has second order of convergency. And now we are going to prove that the order of convergency of Regula Falsi method and secant method is 1.62. So, taking the scheme of secant method or Regula Falsi method, so for n is equal to 1, 2, 3, we will get term by term the approximation to the root of the function. We are starting n from 1 because our initial guess in this scheme is x0 and x1. So if we start from n is equal to 0, by substituting n is equal to 0, we will get x1. So so we have the x1 value. So here we will start for n is equal to 1. For n is equal to 1, you will get x2, and for n is equal to 2, you will get x3 value, and so on. Let us see. Let us consider once again that let r be the exit root of the function where f of r is equal to 0 in the interval ab, and en represent the error in the nth approximation by this method to the root of the function, since as the definition remains the same for the error. So putting these values in the scheme of the secant method, we will get en plus 1 plus r is equal to en plus r. And as well, we have substituted the xn value and xn minus 1 value here. After replacing n by n minus 1, we will get xn minus 1 is equal to aen minus 1. And it is the error in the n minus 1th approximation to the root of the function by using the this scheme. After substituting, and we can cancel here we can cancel this r by shifting to the left side. This r will be cancelled out with this r, and this r can be cancelled out with this r. After cancelling the little bit algebra, what we get en plus 1 is equal to en minus 1 into f of en plus r divided by f of en plus r minus f of en minus 1 plus r. Now we can expand these three terms, f of en plus r, f of en plus r, and f of en minus 1 plus r by using Taylor series. And after expanding it, what we will get these expansions. Now as r is the exit root of the function, by substituting f of r is equal to 0, we will get that. And as well, after substituting r f of r is equal to 0, we can take f prime of r common. When you substitute f of r is equal to 0 and take f prime of r common, so we will get en. And as well, the factorial, the 3 factorial is 3 cross 2, the 4 factorial is 4 cross 3 cross 2 cross 1. As we have studied in FSC or inter level, the n prime is equal to the n uh, 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 the n factorial is equal to n into n minus 1 into n minus 2 into n minus 3 into n minus 4, and so on. So we can write the values of the factorial. 2 factorial will be 2 cross 1. The 3 factorial is 3 cross 2 cross 1, which is 6. So I have substituted the value of the factorial, and as well f of r and minus f of r. So these two will be cancelled out with each other, and from here f prime of r can be we can take f prime of r from these two term common, so we will get en minus 1 because 1 factorial is 1. And now we no need to write 1 factorial or en divided by 1. And here when you take f double prime of r divided by 2 common from this two term, you will get en square minus en minus 1 square divided by 2 into f double prime of r, and so on. So let us neglect all those terms containing nth the error in the nth approximation q, or in the n minus 1th approximation q, because the error is a very small value. And after taking its cube, it will become I think it will be a negligibly a small value, so we can neglect it. After neglecting the values, we will get this. And now we can take this term here, this term common from here, en minus 1 into f prime of r and a square minus b square formula. After expanding this by a square minus b square formula, we will get a square plus b square into a square minus a plus b into a minus b. A square minus b square is a plus b into a minus b. And so we can take en minus 1 from here, and as well from the first term common. And f prime of r can be also taken common, so we will get these values. Now this f prime of r en into minus en minus 1 and f prime of r en minus 1 can be cancelled out. Yet after cancelling these two terms, we will get this. And now shifting this denominator to numerator, and the power will become my negative. Here the power is plus 1, so it will become minus 1. And by the previous result, as we have discussed, that we can expand this term by with the help of binomial expansion. But remember, we can take en common, one en common here, so one en is in the multiplication from this term. And so we are neglecting the en cube terms, and the terms having en p, where the p value is greater than 3 or 3. So we will get this term, and by after multiplication and neglecting the en cube and en minus 1 cube terms, we get this. And now here multiplying this f double prime of r divided by f prime of r with this term and this term, and also this en divided by 2 with these two terms. After multiplying this en divided by 2 with en, we will get en square divided by 2, and f double prime of r divided by f prime of r will be also multiplied with this term. And also this can be we can multiply this with this, so we will get this. Now here this minus negative this term and this term can be cancelled out. So what will we get? We will get, after multiplying minus with this term, we will get this term will become positive, and this two term will be cancelled out. So now from here as well, we can cancel this en with this minus en, so we will get en plus 1 is equal to en into en minus 1 divided by 2 into f double prime of r divided by f prime of r. Now this when we use substitute the value of r in f double prime and f prime, you will get a constant value, and a constant divided by constant will give you a constant value, and a constant multiplied by a constant once again will give you a constant value. So let this constant value consider it that it is equal to c. It may be 1 2 3, it may be any, it is an arbitrary constant value. And now this will become after taking the absolute. Now a dot b absolute is equal to absolute dot b absolute, so we can take the separate absolute of En and the separate absolute of En minus 1. But remember, in addition operator, you cannot apply the absolute to both, because A plus B absolute is less than or equal to A absolute plus B absolute. Now, by the definition of the rate of convergency, we have that if the order of convergency of an iterative method is P, then the error in the n plus 1th approximation to the root is equal to a time the absolute value of the error in the nth iteration in the error in the nth approximation to the root to the power p. Well, these two will be equal, and from this we can write it for en for the nth term. It will be equal to, by replacing this n plus 1 by n, so we will get n here and we will get here n minus 1. So it will be equal to, it is n plus 1 term, it is nth term. So if we take it nth term, it will become n minus 1 term. We will get this. Now, from this, if you take 1 over p power to the both side, this p will be cancelled out with that 1 over p, and here we will get 1 over p, and here we will get 1 over p. After shifting this to the left side, we will get it will go to the denominator, and by taking it to the numerator, its sign will become negative. A to the power minus 1 over p en whole raised to the power 1 over p. Now putting this value in this 1, replacing this en minus 1 absolute by a to the power minus 1 over p en absolute to the power 1 over p, we will get c time en absolute a to the power minus 1 over p en absolute whole raised to the power 1 over p. And again, substituting this 2 in this equation number 3, replacing en plus 1 absolute by a en absolute whole raised to the power p, we will get this. And as well, x to the power a dot x to the power b, we can add the power, so it will become x to the power a plus b. So here the power of en absolute is 1 and the power of en absolute is 1 over p, so we can add its power, so it will become en absolute whole raised to the power 1 plus 1 over p. Now once again, this a is a constant, c is a constant, and a to the power minus 1 over p is a constant value. So let us compare. It may be, it is an arbitrary constant, so we can take it 1, it may be 1, it may be 2, it may be 3. So we need to compare the power of en absolute. Here the en absolute power is p, and here the en absolute power is 1 plus 1 over p, so we can compare these two powers. So p will be equal to 1 plus 1 over p, and now by taking the LCM, it will become p plus 1 divided by p, and after shifting this p to the left side, we will get p square is equal to p minus 1. And now here p square minus p minus 1 is equal to 0. It is a quadratic equation, so you can solve it by with the help of quadratic formula, but I will show you a very simple way how to solve a quadratic equation with the help of calculator. So let us see how to solve. Any quadratic equation can be solved with the help of calculator. So in calculator, you need to press the mode button, and after pressing the mode button, you need to press 5 for equation, and after pressing 5, these are some equations. The first one is a linear equation, the first two, and the third one is in a quadratic equation, which is ax square plus bx plus c is equal to 0. So I will press 3 for a quadratic equation, and after pressing 3, what is the coefficient of the p square or x square? So here the coefficient of p square is 1, so I will press 1, and then I will press equal button. Now the coefficient of p is minus 1, so I will press minus 1, and then I will press the equal button. And now once again the constant value is -1, so I will press -1, and then after pressing the equal button you will get your quadratic equation solution. So this is the quadratic equation solution. Now the order of convergency cannot be negative, so that's why we are ignoring the second solution, and we are considering the first solution. So thank you. So the order of so p will be equal to, after solving this quadratic equation, p will be equal to 1.62, and this shows that the order of convergency of the secant method, or the order of the convergency of Regula Falsi or fixed point iterative, the order of convergency of the Regula Falsi or method of false position, because sometimes we call Regula Falsi method the method of false position. So the order of convergency of secant and Regula Falsi method is 1.62. See you in next lecture. Thank you for watching this lecture.